Hello and welcome to Chapter 3. So Chapter 3 basically adapts two tools that we learned in Chapter 1, the present value and the annuities, and now calls it net present value and annual worth. And these two are introduced as basic decision methods. Then introduces one new tool, and that is the internal rate of return, as you can see on page 47. The internal rate of return is the interest rate that makes the net present value equal to zero. So it's similar to the net present value in the sense that what is the foundation of the tool is bringing all the cash flows to times zero. Net present value is nothing more than the summation of the present value of the cash flows, as we already mentioned in chapter 1. So the summation of all present values is what we now call the net present value. So we know how to do this already. But when we compute the net present value, we use an interest rate to bring those cash flows to times zero. How much are they worth in today's dollars? The task when computing the internal rate of return is basically finding what is that interest rate that would make the net present value of a certain series of cash flows equal to zero. Meaning, in other words, what is the break-even interest rate? What is the minimum return that the project has to provide when measured as a percentage rate in order to make the net present value equal to zero? Then we decide if the project is acceptable for us or not, if that interest rate is greater or equal to the minimum that we require. So for example, let's say we compute the interest rate that makes the net present value equal to zero, and it returns to be 8%. But we want a return of at least 12%. So if our minimum acceptable rate of return, MARR, is 12%, and the internal rate of return of the project that we are evaluating is only 8%, then that's not a good project for us, because it does not return as much as we want. So the rule to accept projects when applying the internal rate of return is to accept projects that have an internal rate of return greater than the minimum acceptable rate of return. When computing the other two methods, the net present value and the annual worth, when we are discounting the cash flows, we are already imposing our minimum acceptable rate of return. So let's say we want 12% return on our investment. We compute the present value of all the cash flows associated with that investment. And if the net present value is greater than zero, then it's generating more than 12%, so it's a good project for us. If the net present value ends up being negative, then it's not worth it, the project, because it does not generate the minimum return that we want. So basically the decision rule when applying the net present value is the net present value has to be greater or equal to zero. Same thing when we are computing the equivalent annuity. The annuity has to be greater or equal to zero in order to be a worthwhile project for us. If the annuity is negative, then it's not good for us. It's not a good project for us. We reject the project because it's not providing us with the minimum acceptable rate of return, the rate that we used to discount the cash flows in order to compute the annual worth. So in sum, 2/3 of the chapter is pretty much a repeat and a new framing of the materials we learned in chapter 1, namely in terms of computing present worth and annual worth, whereas the new component is basically just the internal rate of return, a procedure to find what is the interest rate that makes the net present value equal to 0. For a change, I'm going to use one of the textbook exercises, those suggested exercises at the end of the chapter, and because it's a quite lengthy one and basically goes over all the tools, and then he has an interesting twist on part D. So let's use this exercise as a reference to review the materials introduced in chapter 3. I gave you enough time to buy the textbook, so I'm hoping you all have it. Anyway, I'm going to read. The Simonson Company is designing, fabricating and assembling equipment for a new process that will put into production. The company will invest $175,000 at time 0 and $125,000 at the end of year 1 in order to get the process ready for use. The process is expected to generate revenue at the end of each of the following 5 years as follows. So we have a timeline here starting at time 2 to 6. These are all inflows. The outflows were those written in the text, namely of $175,000 at time 0 and $125,000 at the end of the first year. Then the question proceeds and states, finally, it is anticipated that the process will have a salvage value of $50,000 at the end of the 6-year period. Meaning, whatever we were using, we're going to sell it, and we're going to get $50,000 for it. So on the top of those $100,000 at time 6, we're going to collect extra $50,000 for selling the equipment. Part A. If the funds are worth 15% per annum, what is the present worth of this project? Is the process economically acceptable? So you're basically saying, find the corresponding annuity to this series of varying cash flows using a discount rate of 15% per year and check if it's positive. If it's positive, the annuity, then is economically acceptable. If it's negative, reject. Part B. What is the internal rate of return for this project? So we need to compute the interest rate that makes the net present value of this series of cash flows equal to 0. And then the question proceeds by stating, does this internal rate of return give a consistent interpretation with the present worth? So we have to find an interest rate that is greater than 15%. Only then the project is acceptable. And if the internal rate of return is lower than 15%, then the project is rejected. And we need to then to assess if we reach the same decision using the present worth or the internal rate of return. Basically saying if A and B give the same recommendation. Part C. What is the annual worth of this project if funds are worth 15% and the annuity runs from time 1 to time 6? Is this a result consistent with A? So now use the annual worth method, the annuities, to find out if the conclusion of accepting or rejecting is the same as the previous question A. We'll have the opportunity to check if it's consistent with part B as well. Then lastly, part D. Suppose for argument's sake that one wishes to compute an equivalent annuity that is deferred one period as compared to the one in C above. That is, it runs from time 2 to time 6 instead of running from time 1 to time 6. What is the annual worth in this case if the funds are worth 15%? So a little twist on when the annuity is going to start. So he's going to force us to find a new annuity and to adjust the value. You will see how that is done. Then you have the solutions below. So this is the timeline from exercise 9 on page 50. The interest rate for minimum acceptable rate of return is 15%. Minimum acceptable rate of return. And the project involves $175,000. This is all in thousands. Invested at time 0, $125,000 invested at time 1, and then we start collecting profits. $30,000 at time 2, $75,000 at time 3 and 4, and $100,000 at time 5 and 6. Then on the top of this $100,000 we sell this investment and we get $50,000 for it. Part A is find the present worth. The same is to say net present value. Read the textbook because there are different terminologies for the same thing. This is known as net present value or present worth. So net present value is the summation of all present values. So we're gonna discount the first cash flow using the mother of all formulas. This one will be 175 itself, but for the sake of having it here explicitly is 175 divided by 1 plus the interest rate to the power of n, the interest rate being 15%, and the n 0 because it's happening at time 0. Then we're gonna have the next cash flow, which is also a negative cash flow, and we're gonna discount it 1 year. So we're gonna use 1 plus the interest rate, which we know is 1.15, 1 plus the interest rate, discounted once. Then we have the next cash flow, which is positive, and we discount it 2 years. Bring all these to time 0. So then we would do the same for the cash flow at time 3, discounting it at 15%. The same cash flow happens at time 4, so that's discounted. At time 5 is 100. And at time 6 is 150, the summation of these two. Discounting it 6 years at 15%. And that's how you get a value of negative $54,249. So if we impose a return of 15% as the minimum that we want, this project is not worth it. It will give us a loss of $54,000. So this is less than 0, therefore reject this project. Now part B is asking us for the internal rate of return, given that the minimum acceptable rate of return is 15%. Basically the setup is the same. The issue is we want the net present value, we want this to be 0, we force it to be 0, right? Leaving the variable that is going to make this equality hold to be the interest rate. So instead of putting the interest rate of 15, we're going to leave that as an unknown and solve this equation for the interest rate. So what is the interest rate that makes the net present value of all the cash flows equal to 0? So use your solver and you get that the interest rate, which we call the internal rate of return, because it's the specific interest rate that makes the net present value equal to 0, this interest rate would be 0.09097, with the same is to say 9.10, rounding it. Okay? Note that the textbook has a typo. It states 9.90. I think that the issue was they probably skipped this 0 when they were doing it. So note that this specific solution in the textbook, the correct one is 9.10. And is it a good project or not? No, it's not a good project. To be a good project, this rate will have to be greater than 15%. And it's not. The internal rate of return here is smaller than the minimum acceptable rate of return. The 9.10% are smaller than the minimum that we want. Therefore, reject project. So again, internal rate of return. What is it? Well, the internal rate of return is basically the interest rate that makes the net present value equal to 0. That's the concept. How do you compute it? You set up the equation as if you were to solve for the net present value. You leave the interest rate as an unknown, and you force the net present value to be equal to 0. Then use the solver to find what is the value for this variable that makes this equation hold. That's what we call the internal rate of return. Second step, evaluate if the project is acceptable or not. The decision rule to be acceptable is that the internal rate of return must be greater than the minimum acceptable rate of return. If it was greater than the minimum acceptable rate of return, we would accept the project. But in this case, it is smaller. The internal rate of return is 9.10, the minimum that we want is 15, therefore we reject the project. So that's pretty much it about the internal rate of return. The second part of the question asked, does this internal rate of return give a consistent interpretation with the present worth? In this case, yes, because they both rejected it. However, that does not need necessarily to be always the case. Both the net present value and the annual worth are dollar-based tools. The net present value gave us a dollar amount, in that case was negative $54,000, so it was a dollar amount, whereas the internal rate of return, what it gives us is a percentage. As we're gonna learn later on, methods based on absolute value, which is the terminology we use to refer to dollar amount methods, do not need always to be consistent in terms of decision with the methods based on relative value. That's the terminology we use for evaluating projects based on percentage return, not dollar return. However, in this specific question, they did give a consistent answer. They both said reject the project. I just want to alert you that this does not need to be necessarily always the case. Later on, we will discuss the reasons why. Later on means in chapter 6. We're gonna come back to this issue. So note that this was part B, the internal rate of return question. Now moving to part C. The part C asks, what is the corresponding annuity to this investment? What is the annual worth if we still want a 15% annual return? So to compute an annuity, you learn in chapter 1 that you can do the present value approach or the future value approach. Recall, you have the present value of an annuity formula and you have the future value of an annuity formula. So you can opt, if nothing is explicitly stated about forcing you to use one or the other. Given that in part A we found that the net present value was equal to 54,249, then for part C I recommend using that value instead of computing again everything for the future value, because remember this is the summation of all present values, so I can use in part C the present value of an annuity formula from chapter 1 in order to find the A. What is the annuity that goes from time 1 to time 6 that has equivalent net present value? So we're looking to solve this equation for A. We would impose the present value to be the 54,249 we found from part A. Leave the A as the unknown, that's what we want to find out. 1 minus 1 plus the interest rate, which is 15%. This to be allocated across 6 annuities of equal value, divided by the interest rate. So the A is negative $14,335. Okay. So again, less than 0, then reject. So if you were going to use the net present value or the annual worth, they will give you both a reject answer. And these two methods, because they are both based on dollar amounts, they will have to be consistent. If the net present value rejects, the project, then the annuity, the annual worth method, also has to reject the project. If the net present value would accept the project, then the annual worth method would also have to accept the project. If they are not consistent in their decision, then you did something wrong and you need to review, find out where is the bug. But the point being that because they are methods based on dollar amount, they have to be consistent. They have to produce the same recommendation. The internal rate of return was based on the percentage, not on the dollar amount. That method does not need mandatorily to be consistent with the net present value, the annual worth, or even the net future value that we're going to learn later on. Or better, we already learned about the net future value because it's the summation of all future values. It's just that method is not mentioned in chapter 3, but it's going to come back later on. So this is the annual worth method. Now, part D poses an interesting challenge because what it says is, okay, now find me an annuity again, but the annuity only starts at time 2. So instead of having 6 annuities, we just have 5 annuities. Find that annuity, given the same premises, the 15% interest rate. So again, from A, we know this. Right? We know that at time 0, whatever these annuities are, they will have to have the present value of the negative 54 to 49 at time 0. And the present value of an annuity formula that we learn in chapter 1, this is built for end of the period annuities, which are annuities that start after the first time period being 0 usually, right? So this looks okay in the sense that, okay, first time unit there's 0 and then the annuities start being paid off. So in order to use this formula, I need to have a present value at this point. This formula does not apply in this scenario, in what you have at the end of the first period 0. No. You need to have at the end of the first period an annuity, and that we observe here. But to use this formula, given that our n is going to be 5 annuities paid off, then we need to bring this present value to time 1. So this is the present value at time 0. And therefore, the present value at time 1, it's equal to that amount times 1 plus the interest rate. So at time 1, the present value is 62,386.35. This is the present value I can use in my annuity formula. 62,386, not the 54. Why? Because my formula matches these kind of scenarios. Nothing at time 0 and then they start being paid off. So I need to have a present value at this point. The one that we had from part A was the present value at time 0. So I just need to compound this present value once, bring it here, and then I can use my formula. So we're going to use the present value of an annuity formula. Plug this present value, which is negative, right? It's negative. So negative 62,386.35. Then make this equal to A, the unknown, times 1 minus 1 plus the interest rate, which is 15%, to the power of 5 is the n. 1, 2, 3, 4, 5. Spreading this present value across 5 equal installments, then divide by the interest rate. And this is how you get, I have to take this out of here, this is how you get this new annuity to be equal to negative $18,611. So a little bit of engineering here, financial engineering, nothing major, but it requires you to reflect on how to use the tools that you are already equipped with in order to get the right answer. The key to all this is to have the timeline drawn. Once you visualize it, then you have the tools to solve anything. The key is to have the timeline and visualize it, what you can do. That's all for chapter 3.